So a couple keys to interpreting these PES plots is number one, the x-axis is in decreasing energy. Unlike a typical graph, as you go out farther to the right, it's increasing numbers. Now, there's a couple reasons for that. And then the y-axis is the relative number of electrons found in these orbitals. So knowing that, this kind of fits with the order left to right as you would write an orbital diagram. So for any atom other than your hydrogen, helium, lithium, and the first few elements, they're always going to start with this electron configuration of 1s2, 2s2, 2p6. And once you get past neon, you're always going to see the characteristic of 2 electrons there. So that's your 1s electrons, and that's your 2s electrons. And since this is 3 times the height, in order to have any of these electrons on the outer part of the atom, you're going to have to go through these lower orbitals. So this is going to be your 2p6. So anytime we plot an atom that has more electrons than neon, you're going to automatically see these 3 sets of bumps. Now they're not always going to be at these numbers because these core electrons can shift inward or outward depending on the nuclear charge. And on that note here, you also recognize that this is not drawn to scale. How can that much be 1 and then that same amount be 10 and 100? So these are exponentially scaled. That's not really critical in solving these problems, but just something that's important to keep in mind is not drawn as this is. Sometimes you'll see this disconnected thing to also let you know it's not drawn to scale. All right, well, let's continue with this. This one here is going to be that's the same height as these, right? So what orbital holds 2 electrons? That must be your next s orbital. So that's your 3s2, right? Those are 2 electrons in your 3s orbital. And what orbital can hold 3 times that? So this is 1, 2, this is 3 times the height of an s orbital. That must be your p orbital. Right? If you follow Aufbau's principle, your 3 p's come next. Now this one is half the height of the s orbital. So it must mean there's only 1 electron in that orbital. So it doesn't tell you what orbital it is. So you'll have to follow Aufbau's principle. Right? So you could say maybe is it the 3D? Well, if you follow Aufbau's principle, or if you follow the periodic table, you know 4s comes next. And again, that height tells you there's only 1 because it's half the height of what the s orbitals can hold. So this is going to be potassium. There's your answer. And we just explained the relative. I'll make that clearer. So here is, oh, I thought I had a periodic table. I'll be right back. Okay, so here's your periodic table. There, we know it's potassium, right? Because that's in the 4s, and it's the first. Okay, that's another topic. So we're gonna leave it at that. You can also count the number of electrons, and all of these electrons superscripted add up to 19. All right, let me make sure I explain the location. So the location of these peaks is determined by the relative positions on the x-axis. So here, even though this is the highest energy, you know that's written left to right here normally. So that's your highest. These core electrons would require the highest amount of energy. Or you can say the rightmost peak represents your valence electrons because they're the ones that are going to be requiring the least amount of energy to remove. All right, the relative intensities, they match up with the capacity of each of these orbitals. All right, S is going to hold 2, so that's going to be 2. They don't label these for you, but they could. That's 6, so that would be 1, and then you can fill in the rest here, 3, 4, 5.